Okay, here we are in section 4.6. We're going to talk about projections and the Gram-Schmidt process. This is an awesome section, and as we are kind of starting to see, we're taking some ideas from the very beginning of the course and really diving deeply into them and getting some kind of powerful tools. This process here is going to lead to a really special type of basis for a vector space that's really helpful, and it's a cool process. So let's talk about who even Gram and Schmidt, these two different mathematicians, are. This is Mr. Gram. He is a Danish actuary from like the 1800s, early 1900s, so we know he's awesome. And this is Erhard Schmidt. He is from Germany, and the two of them together are going to come up with this process. But in typical math history drama, actually the process that they're famous for was used earlier by a Frenchman named Laplace. So Laplace lived before either of these guys, and he did some work that led to the whole process. It doesn't get any credit in the name of it, but we should give him a little shout out here. So each of these guys was instrumental in this process we're going to highlight today. A lot of good stuff came out of this. And we're really going to talk about the idea of a basis again, and we're going to look at different types of bases. And so this should be on your mind. Remember that a basis is this sort of really efficient scaffolding for a vector space. It's like the most efficient way that you could build a vector space. It's a set of, it's not the whole vector space, it's a smaller set of vectors inside the vector space that are able to build the whole vector space just through linear combinations. And a vector space can have multiple bases, but interestingly, each of the bases in a vector space has the same dimension. So we've seen that before back in chapter 1. So just kind of as a hint, a preview, a little spoiler, we're going to be building some important types of bases with this process for any vector space. And the first big idea that we need to talk about are projections. So here's the basic idea of a projection. You have two vectors. Here's a vector u, and then you have some other vector, we'll call it v, and it's up here, just sitting around. So here's the basic idea of a projection. Say that we wanted to talk about the projection of v onto the vector u. It's basically how much of the vector v is pointing in the direction of the vector u. So how much of the vector v is pointing in the direction of u? Another way of thinking about it is, what if the vector v just totally collapsed onto u? And as it collapsed, it doesn't even keep its length. It just like drops. And it's not like it drops like this. It just drops straight down. And as it drops straight down, it kind of sheds some of its length and becomes, actually in this case, shorter than it was before. But it just drops straight down onto u in a way that's going to be a right angle. Okay. One place that you'll see projections is when you're talking about or analyzing forces, where you want to know like the physical force of, or the physical effect of a force in a certain direction. So the physical effect of this force, but in this direction. So that would be an example of a projection. So we're going to take v and just drop it straight down. It just collapses onto u. And what we're really interested in then is, what's this vector that results from that projection? And it's a new vector. It's the projection of v onto u. So this new vector is written like this, the projector of v onto u, and we read it as projection of v onto u. And it's this guy right here. So we could ask ourselves, could we find what this vector is? If we knew, say, the vector u, we knew the vector v, and say that we also knew the angle that was between them, just knowing that much, could we find the projection of v onto u? So this probably falls into the category of things you really didn't know you wanted to know, but this is something that we are interested in for the future. And so we're going to ask ourselves, So can we find this new vector, the projection of v onto u, and say that all we know is we know what the vector u is, we know what the vector v is, and we know that angle alpha between them. And let's call this O, like for the origin. We'll call this B up here, and we'll call this point right here A. And so we're really looking for the vector OA. So the answer is yes, we can find it. And the way we start is we're going to find the magnitude of this vector, the length of this vector, and we call that just OA without the little vector sign. We're just going to find the length of it first. That's going to be our starting point. And we're just going to use some trig to find the length. I mean, we can easily find the length of v because we know what this vector is. We know this angle, so we're going to use cosine. Let's see, cosine of this angle would be adjacent over hypotenuse. So that's not too hard. We can easily find this length. Okay, so we know that the cosine of alpha is going to be adjacent over hypotenuse is OA over OB. So another way of writing that is the length OA is cosine of alpha. Now OB is just the magnitude of the vector v, and we've written that before as this is the norm of v, or the length of v, or the magnitude of v. Those all mean the same thing. So a long time ago, at the beginning of the course in section 1.6, we introduced the idea of a norm of a vector, and this was the symbol for length of a vector, norm of a vector. This was the formula we were going to use. You basically just square each component of the vector, add it together, and then take the square root. Back in that same section, we also were able to talk about the angles between any two vectors, and we went through and found out that this was the cosine of any angle between two vectors was this right here. It's their dot product divided by each of their norms. So this guy is going to be really helpful. We're going to use this guy right now. So we're going to use this old fact about the cosine of an angle, and here we're talking about alpha. Back there it was theta, but it's the same idea, the angle between two vectors. So I'm going to take this old fact and just put it right in here for the cosine of the angle between those two vectors. I'm going to use this right here. And you can see why that's going to be helpful because we've got some things that will actually cancel. Okay, so now I'm going to say that OA is, instead of saying that it's the cosine of the angle, I'm going to now say it's u, the vector u dotted with the vector v over the norms of those two vectors. And okay, really quickly, this is a dot product, but this is just a straight multiplication. How do I know the difference? Because these guys are just real numbers, and you're just multiplying two real numbers. This is a vector dotted with another vector. It wouldn't make any sense to multiply two vectors. We don't know anything about that, but we do know the dot product of two vectors, how to take that. So these are different things here, and we know they're different because of the context of what we're dealing with. Okay, back to, we still have to have this guy. All of this was just the cosine of the angle, but right now we need to add this guy right here. He's part of the length of OA. Okay, so that's good. Now we can go ahead and start canceling some things. Norm of v is just a number, so we can cancel that. And we see that the length of OA is all of this right here. So we can say that OA equals u and v dotted together divided by the norm of u. Okay, that's the length of OA, the magnitude. Okay, now that I know the magnitude of OA, here's our basic idea. What we're going to do is, I know how long this is, but I don't really know the coordinates of this vector. That's all that I know is how long it is. If I want to find the coordinates of this vector, here's our strategy. We know how long it is. We're going to take the vector u, whose coordinates we do know, and we're actually going to smush it down to be just a unit vector. So here's the unit vector of the vector u. We're going to know these coordinates, and then we're going to multiply it by the length of OA, and that will get us the coordinates for the vector OA. So let me say that one more time. Our strategy is we're going to take the vector u, we know these coordinates, and we're going to smush it down. to be a unit vector. Why a unit vector? Because this is the vector in the direction that we want that just has length 1. So if we multiply it by the length of OA, it'll get us the whole vector OA. It's in the direction we want already. Just multiply it by the length of OA and we will have what the vector OA is. So what we're going to do is, we already know how long OA is. We went through all this work here to find the magnitude of OA. We are then going to multiply that number by the vector that is 1 unit in length in the direction of the vector u. All of this work will give us what the vector OA is, which was the original thing. We really wanted to find that projection. We spent a lot of time finding the length of the projection, and now we're going to take the vector u, smush it down to a unit vector, and multiply that unit vector by the length of OA. All of this will give us that projection. So I now have this tiny bit of room that I'm going to finish this whole process off out, and we're going to find what OA is. Okay, so if I have this unit vector u, and I want to smush it down to just be 1 unit long, how about I divide it by its norm, its length? This right here will give us that little vector of 1 unit in length, but in the direction of u, because we've divided off the length of u. We have u, and then we divide it by its length, and so it just becomes a little tiny 1 unit vector in the direction of u. Okay, that's awesome. We knew we wanted to do that much. Once we have this little tiny 1 unit vector, we need to multiply it by the length of OA, and that's this guy here. And then we'll have the vector OA. So I have my vector that's just 1 unit long, and it's in the direction of u. I take that and multiply. This is just a number. This is just, it's not a vector, it's just a number. This is the length of OA. I'm going to multiply this guy by the length of OA. So length of OA, I was really hoping to finish everything off in this corner, but we'll have to go to the next page. These here are all just real numbers. And this is a vector. One thing we did learn back in 1.6, I don't really expect you to remember it, that we've learned so many things, but you could go back and review. If you take the norm squared of a vector, that's actually the vector dotted with itself. So we'll use that fact now. So I'm going to take all of these real numbers and kind of try to mush them together. Whoops. U, the vector u dotted with the vector v. And then on the bottom we have the norm of u times the norm of u, but that's just u dotted with itself. Okay, so all of that is a real number, and then we've got little old vector u. And we have just found the projection of the vector v onto the vector u. This part here is a real number, just some scalar, and this part here is a vector. So we have just found what this vector is, and it makes sense that it would be in the direction of u, but some proportion of u. So we can do this for any two vectors, u and v, and you don't have to be in R2, you can be in R17, you can be in any dimension vector space or any type of vector space and still find the projection of one vector onto another. All right, lots of awesome theory. Now let's put it to work with an example. Find the projection of the vector v, 7, 4, onto the vector u, 1, 2. So here's a picture of what's going on. Here's our vector v, and here's our vector u, and we want to project v onto u. And at first you think, whoa, that's u is too tiny. You can't project v onto u. We really are going to drop, let's see, let's get this right, v right onto, well, the span of u. Where would it land? So we really do look at the span of u, the vector u. And if we drop to v just perpendicular and shed off some of its length, then where would it land? So the vector that we're interested in looks something like this. It's going to be shorter than u because it's projecting onto the span of u. This is the vector that we want to find right here. And we'll use this guy right here. So we'll use this formula that we've spent so much time developing and find that projection of v onto the vector u. And we know that it starts off with taking the dot product of the two vectors, u and v. So in this case, that will be the dot product of 1, 2 with 7, 4. And then in the denominator, we have the dot product of u with itself. And that number, it'll end up being a number, is multiplied by the vector u. Okay, the dot product of 1, 2, 7, 4 is just 1 times 7 plus 2 times 4, so that's 7 plus 8 over 1 times 1 plus 2 times 2, and that'll be over 5 times the vector 1, 2, and that's 15/5, which is 3 times the vector 1, 2. So the projection, it looks like, is the vector 3, 6. And does that sound reasonable? 1, 2, 3, 1, 2, 3, 4, 5, 6, about right here. So is this vector a reasonable answer to get for the projection of u onto v? And definitely it looks like it. So we can draw that new vector 3, 6. It's about right there. And this is the projection of v onto u. So 3, 6 is the projection of v onto u. This vector right here. So we now know what projections are, and we know how to find them. Now that we know about projections, we're going to go through a series of true-false statements all about bases, just to refresh our minds on what a basis is and what the characteristics are. And our first statement is 1001 is a basis for R2. So is that true or false? That's definitely true. This is, if anything is a basis, this guy is. It's the standard basis. So it is the standard basis. And for Rn, it would be similar. You know, each of the vector spaces Rn have a standard basis. The next statement is 1, 3, and 2, 4. Those two vectors form a basis for R2. True or false? Here again, the answer is true. And the reason this is true, we know that any basis in R2 has two vectors. We've got two vectors. And these are two vectors that are linearly independent. That's so important. How do I know they're linearly independent? Well, in R2, it's actually super simple to tell. If two vectors are linearly independent, you just have to make sure that one of them isn't the multiple of the other one. This only really works in R2 because when you get into higher dimensions, it gets trickier to tell whether two things are linearly, well, not two things, but multiple things are linearly independent. Anytime you're trying to tell two things, one of them has to be the multiple. But when you have more elements that you're trying to detect linear independence, that gets a little bit trickier. So anyway, R2, it's easy to see these are linearly independent. One is not the multiple of the other. And if you have two linearly independent vectors in R2, they are a basis. So we can say this is true because we know that they are two linearly independent vectors in R2, and that guarantees a basis for R2. It wouldn't be the same in R3. In R3, you have to have three vectors that are linearly independent to be a basis, and in R3, it's harder to tell, you know, if those three vectors are linearly independent, but these guys definitely are. Okay, our next statement is that the vectors 1, 3, and 2, 6, they form a basis for R2. So is this true or false? This is definitely false, and the reason it's false is because these are two vectors that are linearly dependent on each other. This guy is just double this vector. So if you had, 1, 3 is this vector right here, 2, 6 is this vector up here, there's no way for those two vectors to, through some linear combination, to create a vector out here. They will only create vectors on this span because they are essentially, these two vectors have the same span, that one-dimensional span. So they can't form a basis. They don't hit enough other vectors in R2. So this is false because all you can construct are multiples of the vector 1, 3. You can't construct a lot of other vectors in R2. And a basis has to be able to construct any vector in that vector space. Okay, the next statement, 5, 8, the vector 5, 8 is a basis for R squared. So true or false? This one's definitely false. There's not enough. I mean, this one vector cannot generate all of R2. It's just not enough. We know that there has to be two vectors for a basis in R2. The next statement, 1, 0, 0, 1, 1, 1 is a basis for R squared, R2. True or false? And these guys definitely will generate all of R2. but this statement is false because there's too many of them. This guy right here is actually a linear combination of these two. So these are linearly dependent vectors, and you can't have that in a basis. And plus we know that a basis in R2 should only have two vectors. Okay, the next statement, a basis spans the vector space and is linearly independent. So true or false? This one is true. This is the definition of a basis. This is exactly what it means to be a basis. These two conditions, spanning and linearly independent. Last statement, there are an infinite number of bases of R2. Well, we know this guy's 1, and we know this guy's 1. This is true. There are an infinite number, and you can think of any set of two vectors in R2. If they're linearly independent, they will form a basis. So 1, 0, 0, 1 is a basis of R2. 2, 0, 0, 2 is actually also a basis. Really any two vectors, A, B, and C, D, that are linearly independent. And one way we can describe that is such that, okay, so this symbol means such that AC minus BD does not equal 0. And this actually stems from the determinant not being 0, and that would force these to be linearly independent. Any vectors that satisfy this condition will be a basis for R2, any linearly independent vectors. So there are definitely an infinite number. All right, this was a good review of the idea of a basis and what it has to be. One note I want to make before we move on. In the vector space Rn, whatever size it is, any set of n linearly independent vectors is a basis. There have to be n of them, and they have to be linearly independent, and you'll have a basis. So this is just a fact to remember. Okay, we're really close to being able to talk about the Gram-Schmidt process and what it is. We need one tiny theorem before we talk about it. And this theorem is really short and sweet, but it's super powerful. So the theorem says an orthogonal set of vectors. So you guys remember what orthogonal means. It means two vectors in 2 dimensions, they're perpendicular to each other. In 3 dimensions, they're perpendicular to each other. And in more dimensions that are hard to visualize, the idea of vectors being orthogonal is their dot product always equals 0. So we have a set of mutually orthogonal vectors. So take any two vectors in the set and their dot product will be 0. In R2, it's like they're at right angles to each other. So an orthogonal set of vectors is linearly independent. So that's pretty cool, because if you have a set of vectors and they're all orthogonal, then you automatically know they're linearly independent. So that's a big idea. We don't go through all the proofs of theorems in this course, but this one we are going to go through. It's really a beautiful proof. Okay, so we start off with these vectors, this set of m vectors. And we'll say that they're all orthogonal to each other. So what we have to do is prove then that they're linearly independent. So we're going to think about a linear combination of these that produce the 0 vector. So some constant c1 times the vector v1 plus c2 v2 plus dot 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 all the way to some constant cm vm. So a linear combination of all the vectors, and it equals the 0 vector. And we know from a long time ago that if you have a set of linearly independent vectors like vi's, then this only happens if each of these guys is 0. That is one test, one way to prove that vectors are linearly independent, that in a situation like this, the ci's must be all 0. And if it only works that this is true when the ci's are all 0, then you've proven linear independence. So it sort of goes both ways. So I'm going to take this linear combination of all my vectors, which is equal to the 0 vector, and I'm going to sort of prove that each of these C's have to be 0. And the way I'm going to prove it is I'm going to take some random vector in the set vi, and I'm going to dot product it with this vector, and then dot product it with the 0 vector. So same thing on the left and the right. So when I take this first dot product with this vector and this vector, I get C11 vi dotted with v1 plus c2 vi dotted with v2 plus all the way through to cm, that constant, times vi dotted with vm. And then I get, on the right side, v dotted with 0 is just the number 0, if you think about what's going to happen in that dot product. Okay, so each of these terms is a number, because when I take the dot product I get a number out. They started as vectors, but these are numbers now. And because it's an orthogonal set of vectors, I know that vi dotted with any other vector in the set has to equal 0, because that's what it means to be orthogonal. So that's going to be 0, this is going to be 0, this is going to be 0. There's one time though that it's not 0, and it's when somewhere in here when vi gets dotted with itself, and we'll see what happens in that case. But for all of these other guys, because they're orthogonal vectors, this becomes 0, this becomes 0, this becomes 0. But somewhere in here there's a ci vi that's getting dotted with vi, and that's not 0 because these guys are not the 0 vector, so a vector dotted with itself will not be 0. And what we're left with is everything else is gone except this term here. And so we have that this term here equals 0. So it must be true that this equals the number 0. And I know that this part is not 0 because a vector dotted with itself, if it's a non-zero vector, which all of these are, cannot be 0. So this guy right here, ci, he must be 0. Because we're creating, when it gets multiplied, we're creating a 0 here. So because this is really taken in the general case, ci could have been any of these c's, and so all of the ci's are 0. So all the ci's must be 0, just because we could have used this argument really on any of the ci's that we were using right here. And if all of the ci's must be 0, the vectors are linearly independent. So we must, that set of vectors must be a linearly independent set of vectors. And all we started with was a set of orthogonal vectors. So this whole proof shows that orthogonal sets of vectors are linearly independent. That's a cool fact. So this was sort of an old fact that we knew about linear independence that we used. And all of this was just a proof of this fact, that these are linked. Sets of orthogonal vectors are linearly independent. Okay, we are just like inches away from the Gram-Schmidt process. There's just one more question I got to ask. So a set of n orthogonal vectors in Rn all have length 1. So picture that in your mind. There's n of these vectors. They're all orthogonal, and we know that's pretty powerful. And these ones in particular only have length 1. So actually I lied. I have two questions, but the first question is that set a basis for Rn? And the answer is absolutely. You have n orthogonal, but that also means they're linearly independent, we just proved. So n linearly independent vectors in Rn, definitely a basis. So the answer is absolutely they're a basis. You have n linearly independent vectors in Rn. So the second question is, what would be a good name for that type of basis? We have a basis that's orthogonal, and this kind of weird new condition that I put on, that all the vectors have length 1. So I should say that, I can't remember if we've used this term before, but if a vector has length 1, it's what's called normalized. If you see the word normalized, it's a vector of length 1. So a good name for an orthogonal basis where all the vectors are normalized would be an orthonormal basis. And an orthonormal basis is a really awesome type of basis to have. The standard bases in Rn, you know, the 1, 0, 0, 1 for R2, that's an orthonormal basis, but it's not the only one. There's there's an infinite number of orthonormal bases in the vector space R2, R3, R4, whatever. So right now we're going to think for a minute about a basis in the vector space R3. Okay, so the Gram-Schmidt process works for any vector space, but I'm going to show it to you in R3. We have these three vectors, 1, 2, 3, they're all different sizes, going in different directions, but they are linearly independent. And this is a basis for R3. I'm holding it in my hand. What Gram-Schmidt is going to do is it lets one of them stay put. So we'll let this guy stay put, this vector. And it moves all the other vectors in that basis until they are orthogonal to this guy and orthogonal to each other. That's the first part of Gram-Schmidt. So we now have an orthogonal basis. And the second part of Gram-Schmidt is you're going to take each one and normalize it. So literally, like, make each of them just 1 unit in length. And we're going to snip off until each of those vectors is 1 unit in length and orthogonal. And that's the whole Gram-Schmidt process. We start with a random basis and we create an orthonormal basis. We're now ready to talk about the Gram-Schmidt orthogonalization process. This process will take a random basis of a vector space V, something that's not really anything special, just some random basis. And it will transform that basis into a super duper awesome orthonormal basis. So we start with a set of vectors which are some random basis for a vector space V. Now, granted, being a basis is pretty special. It's not every set of vectors that's a basis. So already we're in sort of elite company, but we're going to make it super elite by creating from this basis an orthonormal basis. And we'll take care of the orthogonal part first, and at the end we'll normalize everything. So the first thing we're going to do is the orthogonal part. We're going to take each of this set of vectors, and we're going to move them around a little bit so that they're still linearly independent, but that they become orthogonal to each other. And we're going to let this guy stay what he is. The very first vector gets to stay in his position. So the new vectors that we're creating, the orthogonal set, we're going to call UI, U1, U2, U3. And U1, we're just going to let that equal V1. Now, the second vector, U2, we want this to be an orthogonal vector. And V2 probably isn't orthogonal to V1, so we're going to force it to be. And the way that we force it to be is really the genius of these guys right here. We're going to take V2 and we're going to subtract off the projection of V2 onto the vector U1, sorry. So we're going to take V2 and subtract off the projection of the vector V2 on U1. This step right here really displays the genius of the whole method, so I want to give you a little justification for why you would even want to subtract this off. Say that this right here is that first vector in the basis. So say that these are the first two vectors in that original basis, the one that we were just handed, you know, and this is V1 here, the orange guy, and the blue guy is V2. Well, we decided in this process that we were going to let V1 stay as he is, so we actually get to call him U1. He's staying what he is. So this is the new U1. Okay, but somehow we need to make this guy perpendicular to that. So here's the idea. We're going to find the projection of V2 onto U1. It's this vector here. And we're going to then subtract that vector from V2. The subtraction will look like, remember how to subtract vectors? It will actually look like this. You take the vector going in the opposite direction, you start at the head of V1, and V2 minus the projection of V2 onto U1 ultimately will be this right here. So let me run through that again. We're starting with V2. We want to make it orthogonal to U1 because we need orthogonal vectors. And the way to make it orthogonal is to find the projection of V2 onto U1. So that's this right here. We know how to find those projections. And then we're going to kind of flip this vector around, and we're basically subtracting that projection from V2 here. So we're going to take this guy and we're going to subtract it from V2. And when we subtract it, this point right here is the new point. That's the solution to that subtraction. And so that vector looks like this. This is our new, it's what we're going to call a U2 because it is an orthogonal vector to U1 that we've constructed from V2. So this red guy is the projection of V2 onto U1. And to take V2 minus this projection will look like V2. And then starting at this end of the vector, subtract, go the opposite direction, that projection. Once we've done this subtraction of the projection of V2 onto U1, we have a new vector right here. And this new vector is orthogonal to U1. This is the vector V2 minus the projection of V2 onto U1, and it is orthogonal. This is the symbol for orthogonal to U1, which is exactly what we needed. So this demonstration is sort of a little bit of a hint of a proof of Gram-Schmidt, why it works. We're going to call this new vector here U2. And we keep going. We keep producing orthogonal vectors like this. We have U1, we have U2, U3. We're going to see what that is. The way we're going to construct the vector U3, this new vector in our orthogonal set, is we're going to take the vector V3, and from it we'll subtract the projection of V3 onto U1, and we'll also subtract off the projection of V3 onto U2. So I hope you're getting kind of an intuitive feel for why we're doing this. Remember that the projection of this vector is the part of this vector that's going in U1's direction. And by subtracting that off, it's like we're taking that away from this vector and we're just left with what remains. And we're doing that each time. So to create U3, we're taking the vector V3, we start with that, and we're sort of subtracting off the piece of V3 that's sitting on U1, or the piece of V3 that's going in the direction of U2. We want to take those off so they're not going in the same direction at all, but that they're orthogonal to each other. This process continues until you've hit your last original vector, Vn. And to create the new orthogonal vector, we're going to take Vn and basically subtract all the pieces of Vn that are sitting on the other orthogonal vectors, U2, U1, all the way up through Un minus 1. So Un starts as the vector Vn. We subtract off the projection of Vn. Any part of Vn that's going in the direction of U1, then we subtract off any part of Vn that's going in the direction of U2, and we keep doing that until we hit the end. Any part, so the projection of Vn, any part of Vn that's sitting on Un minus 1. And that will force this new vector U to be orthogonal to all of these guys. So this is it. This is the method for creating an orthogonal set. The next step, which is normalizing it, we just take these vectors here and normalize each one. So we divide each one by its length, and then it will be length 0. So next, you're just going to normalize each of these vectors that we've found. They're all orthogonal at this point. We just need to make them of unit length, or of length 1 unit. And that's not too hard. The hard part is really this work in here. So of course, typically for a process like this, a computer is going to do a lot of the work. If you were in a vector space that was 73 dimensions, this would be a tremendous amount of work to do, and we would never do that by hand. Nobody does. I guarantee you nobody in the world does this by hand with 73 dimensions. But we are going to get some practice with maybe 2 or 3 dimensions finding an orthonormal basis. Okay, now we're going to take everything we learned and work through this example. We're given a random basis for R3, and I guarantee you this one is not orthogonal and it's not normalized, but we're going to use it to create an orthonormal basis. So I'm going to stick these guys right here just so we remember what it is exactly we're doing. This is the whole process for Gram-Schmidt, piece by piece. And then I put this guy here just because I need to remember what the formula for a projection of a vector v onto another vector u is. All right, we're ready to go. So Gram-Schmidt says basically your first vector you get to just keep as it is. So this vector, we're going to let that be, it's the first vector in the random basis. We're going to let it be the first vector in the orthogonal basis. Good. So we only really need 3 vectors. We've already got the first one. And the second one will come by taking the original second vector and subtracting off the projection of this guy onto this vector. And as we're working, I'm going to call these guys, I'm going to call it V1, but it's also our new U1, and then I'm going to call these guys V2 and V3. And our goal is to get U1, U2, and U3. So this second orthogonal vector is going to be the old second vector minus the projection of V2 onto U1. And in this case, that's 2, 0, 1 minus, the projection of V2 onto U1 will be the dot product of V2 with U1 over the dot product of that U1 with itself in the direction of U1. And this is 2, 0, 1 minus, dot product is 2, 0 plus 1, that's going to be 3 over, and this dot product down here will be 1 plus 1 plus 1. That's 3 in the direction of 1, 1, 1. So this is essentially just the number 1. So we're taking this vector minus this vector, and that is 2 minus 1 is 1, 0 minus 1 is negative 1, 1 minus 1 is 0. Awesome, we have our second orthogonal vector, and this is it. Here was our first one. All we have to do now is find the third one. Okay, so we're going to find this guy. This was piece of cake to find because there was no work involved. This one was not too bad. This one is going to be kind of bad because we have to subtract off two projections. We really, for this third orthogonal vector, we take the original third vector and we take off any piece of it that's going in the direction of U1 or any piece of V3 that's going in the direction of U2. We need to get rid of those pieces so that it'll be orthogonal to both of these. And so V3 is 2, 4, 5. And then from that, we'll subtract off these projections. And so there's just going to be a whole horde of dot products in here. Here is the first projection. This is the projection of V3 with U1 in the direction of, it's this dot product and then this dot product in the direction of U1. Now this second projection is the projection of V3 onto U2. This is U2 right here. So we're going to take the dot product of V3 with U2, and then on the bottom is the dot product of U2 with itself. And all of that is in the direction of U2. Okay, we've got every little piece. We just have a bunch of arithmetic to go through here, or algebra. Okay, this dot product up here is going to be 2 plus 4 plus 5 is 11. And this dot product here will be 1 plus 1 plus 1. So that's 3, so minus 11 thirds times this vector. And then this dot product here, well, first let's write the vector here, and this dot product here will be 2 minus 4, so that's negative 2 plus 0, so negative 2, and this guy's 1 plus another 1, that's 2, equals 245 minus 11 thirds, 11 thirds plus, this is now a plus 1, 1, negative 1, 0. And let's see, if we go 2 plus 1 is 3 minus 11 thirds. 3 minus 11 thirds is negative 2 thirds. And then we've got 4 minus 1 is 3 minus another 11 thirds is negative 2 thirds. And last but not least, 5 plus 0 is 5 minus 11 thirds. So we've got 15 thirds minus 11 thirds is 4 thirds. This is it. This is, no, not U2. This is U3, our third orthogonal vector. Definitely took a lot more work, but we are now finished. That's awesome. Okay, so we've got these 3 orthogonal vectors, and I promise you that they are orthogonal. If you take the dot product of any 2 of them, you'll get 0. The only thing is they're not normalized yet. We now have this orthogonal basis. And remember that this came from our original basis, this some random basis that they handed us. So this random basis, which, you know, a basis is a big deal. It's not like a random set of vectors. These guys all will be able to generate R3. So that's really impressive that these 3 vectors can do that. But we took it and we made it an orthogonal basis. We're going to take it one more step and normalize each of these. In other words, make them 1 unit in length, and we'll have an orthonormal basis. Okay, remember we're back in early days of class, and this was the norm. This is basically the length of a vector, but I want you to remember how to make it. It's the square root of the dot product of a vector. And so we can find the length of any vector. So hold on to this formula in your head because we're going to use it in just a minute. So I went ahead and did all the arithmetic. The norm of this vector is square root of 3, and the norm of U2 is square root of 2. And the norm of U3, it's not quite as pretty, is 2 square root of 6 divided by 3. And I'm going to take each of these and use them. So with this orthogonal set of vectors, I'm going to divide each element in this vector by square root of 3, each element in this vector by this, and each element in this vector by this, and that will cause these vectors to then be of length 1. So this vector here, I divide by its norm, and I'm going to get the vector 1 divided by square root of 3, 1 divided by square root of 3, 1 divided by square root of 3. I take this vector and divide it every piece by its norm, and I get 1 divided by square root of 2, negative 1 divided by square root of 2, and this stays as 0. And last, I take this vector and divide it by its norm. This division is not quite so nice, but I will get, let's see, negative 2 thirds. If you think of multiplying by the reciprocal, the 3's will cross out, the 2's will cross out, and I will get negative 1 over square root of 6. Second element is identical. And then the third element, 4 thirds divided by this is 4 thirds times the reciprocal of this. The 3's will cancel, and I'll end up with a 2 over square root of 6. And we have now created not just an orthogonal basis, but an orthonormal basis. So we've gone from some random basis to an orthogonal one, orthogonal to orthonormal. And an orthonormal basis is a special thing. It's very special. It's what Gram and Schmidt worked so hard to be able to construct, is not just some random basis, but a basis where every vector will be orthogonal and of unit length. So a perfectly legitimate question is to ask why. Why do we care if it's orthonormal or if it's just some random basis? And one of the most important answers is, and what you'll see in future linear algebra classes, is writing vectors as a linear combination of orthonormal vectors is way easier than writing vectors as a linear combination of a random basis. This is one of the big advantages